Hello. This is Nicholas, and I'm doing a video on the very slick method of stars and bars. And this is a very cool way to do certain types of counting problems. And so I think it's best to kind of teach this by example here. So let's give kind of a real-world example. Let's say we have two kinds of donuts, and we want to buy 12 donuts, a dozen donuts. And let's call these two kinds of donuts A and B. And we want to buy 12 donuts. And basically the question is, how many ways could we buy a dozen donuts given that there are two donuts? So for example, we could buy all 12 of A and none of B, or 11 of A and 1 of B, so on and so forth, down to none of A and all 12 of B. And so this leaves us with 13 ways, because the value associated with, say, A goes from 12 down to 0. And so the number of numbers between 0 and 12 inclusive is 13 numbers. So what this means is that given two kinds of donuts and you want to buy a dozen, how many ways can you do that? You can do it 13 ways, So let's kind of complicate it a little bit. And let's do three kinds of donuts now. A, B, and C. And then we have we're still wanting to buy a dozen donuts. So what we can do, we can start by locking C and then consider what happens with A and B. So, because when we lock C, then we've reduced it to the two kinds case that we've already handled up here. So when we lock C, right, we could either have 0 of C, in which case then we'd have 12 donuts among A and B. And if we have 12 donuts and there's two kinds, we've already shown from above that there's 12 ways for the others to be purchased. I did that again. There's 13 ways, right? From 12 to 0, right? Like how we did up here. So there's 13 ways for the other 12 donuts to be arranged, given that you buy no C donuts. If you buy one C donut, then there's 11 donuts for, you can buy 11 of the A and B donuts, however you want to purchase them. And so it would make sense then that here there would be 12 ways for the other donuts. Because what's going on is that in this particular case, in the two kinds case, we had 12 donuts and two kinds of donuts, and there was 13 ways to buy those two kinds of donuts, namely the number of donuts plus 1. So here we have 11 donuts, and there's two kinds, so there will be 11 plus 1 or 12 ways. So now we see so on and so forth. If we go up to 12 C donuts, then there will be 0 ways to buy the other donuts, right? And so now if we have the three kinds case, the number of ways ends up becoming 13 plus 12 plus yada 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 down to 0, which is the sum of the first 13 whole numbers, which you should know as 13 times 14 over 2, and that's just a number. I'll leave it at that. The number itself isn't so important as the method. So now let's consider 4 donuts. And then this we'll stop considering and we'll move on. So if we have 4 kinds now, A, B, C, and D, and we still want to buy a dozen donuts, how many ways can we buy 12 donuts by purchasing those 4? So let's lock D now, since we have considered the case already what happens when we have A, B, and C from above. So in D, we could say we have 0 D donuts, and that leaves 12 ways to buy the other donuts. And that from up here, we can buy that 13 times 14 over 2 ways when there was 12 donuts. In other words, it's the sum of the first n plus 1 counting numbers or natural numbers, where n is the number of donuts. If we have 1 D donut, then what we're going to end up doing is taking the sum of the first 12 whole numbers, right? We get rid of this extra 13 because we have already bought 1 D donut. And so that leaves 12 plus 13, or 12 times 13 over 2, ways, right? Because it's 0 plus 1 plus ... up to 12, which is 12 times 13 over 2. Okay? And then we go so on and so forth up to 12 D donuts and 0 ways for the other donuts. And so now what ends up happening is that we need to compute this to find the total number of ways. We need to find 13 times 14 over 2 plus 12 times 13 over 2 plus 11 times 12 over 2 plus so on and so forth, plus eventually 0. And there is no easy way to communicate, or not to communicate, to compute this number. I mean, we could take 13, multiply by 14, divide by 2, and then add that to this, and then add it to that, and it could be done, but it would get very messy. And then it would get even worse, because then the next case with 5 donuts would depend on this number. And so what I'm trying to get at is that we need a new way to think about this. We need a new way to think about this. And so let's kind of think about it like this. Let's still consider the 4 kinds of donuts and the 12 donuts that we, as the number that we wish to buy. And so what we're going to do is we're going to imagine 12 slots for the number of donuts that we're buying. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we're going to imagine, we could do it this way. Let's actually, since I called it stars and bars to begin with, we're going to do 12 stars. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and those are representative of the donuts that we buy, of the dozen donuts. And now we have 4 kinds. So what we're going to use now is bars to kind of divide off the different types of donuts. So say we wish to do it even, right? So say this bar right here we put, say these 3 are the A donuts, and then we do 3 more B donuts, and then we do 3 more C donuts, and then the rest is D donuts. And notice the number of bars is always 1 less than the number of kinds of donuts, right? We don't need a 4th bar here or anything. And that's a very important point later on. So what we can now do is consider all of these stars and bars, that's where the name comes from, as their own slots altogether. So we have 12, 3, 6, 9, 12 stars and 15, and 3 bars, making a total of 15 slots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 slots. And so basically it's an argument of symmetry from here. We want to figure out either how many ways of these 15 slots can we choose 3 bars. Well, we can do that 15 choose 3 ways. Or how many ways can we choose the 12 stars within to put these 15 in these 15 slots. And so that is done 15 choose 12 ways. And these two things are equal by the symmetry of Pascal's triangle. And this number is telling you the answer to our original question, right? So another way to think about it is we have 15 slots for all of these stars and bars. So how many ways can you put 15 things into 15 slots? Well, 15 factorial ways. But then we need to divide by a 3 factorial because the bars themselves are indistinguishable amongst each other, right? It's not like this is bar number 1 and then bar number 2 and then bar number 3, right? They're all the same. So we divide by a 3 factorial because that's the number of ways that the bars themselves can be indistinguishably permuted about these 15 slots right here. Likewise, we can't tell the difference between these 12 stars, and so we would need to divide by a 12 factorial, which in essence is just like how the 3 factorial was the number of ways that the bars could be commuted, or I'm sorry, not commuted, permuted amongst themselves in the 15 slots. The 12 factorial represents the number of ways the stars could be permuted amongst themselves in the 15 slots, right? Like, for example, let's say I have, just so I can kind of show you what's going on here, let's say this star's red and this star's blue. Now, in actuality, you wouldn't be able to tell the difference between these stars, but I'm just doing this to illustrate a point. Let's say I have the red star here and the blue star here. Or if I were to consider a separate outcome, I'm not going to draw all 15 slots, just kind of imagine they're there. I could also have the blue star here or the red star here. Now, in reality, these two outcomes are indistinguishable from one another because you can't tell the difference between the stars, right? There is no red star or blue star, they're just all the same stars. And so what that means is that we have, in essence, overcounted. And so we would need to divide by the number of ways that we've overcounted. And so with the stars, that's 3 factorial ways we've overcounted. And then with the bars, that's 3 factorial ways we've overcounted. And with the stars, that's 12 factorial ways we've overcounted. And so the answer to the question is 15 factorial over 3 factorial, 12 factorial, which is 15 times 14 times 13 over 3 times 2 times 1, which is the same thing. The 3, that will leave a 5, that will leave a 7, and so the answer is just 5 times 7 times 13, whatever number that is. And so this provides a much more generalized way of thinking about our problem. If we have k kinds of donuts, and we wish to buy n donuts, and we want to ask how many ways can we do that, well, of course, realize, of course, that n is going to be greater than k, right? If there's only, if there's only one kind of donut and we want to buy if there's like 2 kinds of donuts, but we only want to buy one donut, well, how many ways can we do that? Only one way. So in the case where n is greater than k, then the number of ways to do it, notice, is, n donuts corresponds to n stars, right? And then k kinds of donuts corresponds to k minus 1 bars. And so then the number of ways of doing that is the total number of slots formed, so the number of stars plus the number of bars, which is n plus the k minus 1. And then we can either choose how to arrange the k minus 1 bars, or we can choose how to arrange the n stars. And notice that these two are going to be equal by the symmetry of Pascal's triangle, right? So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So for example, this 4 and this 4 are both the same, right? So that's 0, 1, 2, 3, 4. That's 4, choose 1, which is also 4, choose 3. Both of those reflect a 4, which in a sense, then, in this sense, the method of stars and bars offers an intuitive explanation as to why Pascal's triangle is symmetric, because it's made up of combinatorials, and we have just shown that either way, whether you arrange the stars or whether you arrange the bars, that's the same number of arrangements, right? You're doing the same thing. When you lock in the bars, you lock in the stars because the stars are indistinguishable. And when you lock in the stars, you lock in the bars because the bars are indistinguishable. And so in that sense, this kind of proves this identity not really proves, but it gives intuition for this identity. And now there are more situations that you can use this method of thinking for, let's say, for example, you've got a plus b plus c equals 5, and a, b, and c, they're all greater than or equal to 0. So the non-negative integers. Okay, and we want to find how many solutions a, b, and c there are to this equation. By the way, this is known as a in the business of linear algebra as a Diophantine equation, a linear Diophantine equation, if you're interested in exploring them more. So it's really the same problem, actually, because imagine it like this. We have 5 total stars, 3, 4, 5, and then we have 3 bars, basically. That corresponds to the fact that we have the 3 variables, right? So if we put a bar here and a bar here, that would be basically like saying that, okay, A equals 1 is a solution, B equals 2, and C equals 2. If those are all happening at the same time, then that's a solution. And so the number of stars basically corresponds with what the Diophantine equation is set equal to, and then the number of bars corresponds to the number of variables. And so by stars and bars, this tells you we've got 5 stars, we have 2 bars. That means we have 7 total slots, and we're choosing to put those 2 slots somewhere, or we're choosing to put the 5 bars or we're choosing to put the 2 bars somewhere, or we're choosing to put the 5 stars somewhere. Either way you do it, you're going to get the same thing. And so that number, the 7 factorial over 5 factorial, 2 factorial, which is 7 times 6 over 2, which is 7 times 3, or 21. That means there's 21 solutions in the non-negative integers to this Diophantine equation. And so I kind of encourage you to kind of explore this idea of stars and bars for yourself and see what other types of situations that you can use this method of counting in. It was a very powerful way, and it works very quickly too once you understand the concept behind it. So I think with that,